My name is Simon Johnson. I'm a senior PE, principal engineer here at Intel Corporation. I've been involved in confidential computing now for nearly a decade, starting with software guard extensions, working on that program, and then from there I went on to just recently get engaged with the TDX program, and I'm very happy to be back at OC3. This is my second time. I was here a couple of years ago talking about Intel Trust Domain extensions. And I want to give you a sort of like a brief overview of that technology. But before I get there, I think what I wanted to do was at least do the compare and contrast of the different trusted execution environments that Intel is looking to offer, what the differences between them are, and where and when you might want to choose one versus the other in providing protection to data confidentiality in processing. So SGX is really well known. I'm not going to give an introduction to the technology, how it works. I think it's pretty well understood. It's been out in the market since Skylake came in, which was sort of like the back end of 2015, if I remember correctly. We recently introduced that as part of our Intel Xeon scalable processors for data center at the back end, the beginning of 2021, Isolate, codename Isolate product. And this is really, I mean, it's all about providing separation. All these TEs that we offer do that, but its forte is really about providing the smallest or the smaller trust boundary and reducing the software attack potential to the smallest level, right? That would allow people to put small code that's pretty amenable to inspection, and that you can deploy that in a number of different types of environments, whether that be in a virtual machine, whether that be in a cloud native container, or on directly on bare metal. Now, that has some advantages and disadvantages, right? If you can have a small trust boundary, you've actually got to do some work to get there, and so you may actually have to do some application-specific enabling to get there or tailor that. And the other thing that you have to really be sort of like pay attention to is what the performance overhead, the cost of doing calls in and out of the enclave. That certainly has a fixed cost associated with it, and the more often or the less often you do that, the longer you get to amortize that cost, right? And that all ends up in a performance impact in the end. What we'll be introducing, and we'll talk about when that's going to come available later on, is TDX. TDX is, again, it's still providing this separation from the cloud provider and other tenants that are executing in the platform. But its aim is to reduce the overall porting effort needed for existing applications into those sorts of cloud environments. And that means that it's going to be much more amenable to enterprise-wide deployments, and should be hopefully a way of doing simple configuration rather than necessarily having to understand specific security issues, right? So now the trade-off that you get with this is that you're going to add more software into that trust boundary, right? So your trust boundary is going to be a little bit larger than it is with SGX, right? But it's going to be easier to get there, right? Now, if you have to update your guest and the application, you may need to revalidate that, right? So you need to take those things into consideration. Of course, if you've got more in the TD, then the trust domain, then it's going to be a little the attestation that you're going to get is going to be a little less granular. So those are sort of like the top level compares and contrasts between the two different technologies. Now, oops, one too far. So in graphical terms, right, the importance of the TCB, I mean, as security folks, right, we get we find this very, very important to talk about, right? So if you look at how much software you have to trust today, if you're deploying into the cloud, right, not only do you have your applications and your guest OS that's having access to your data, but all the things below that are also actually in the trust boundary too. And so what trusted execution environments it does is to look to minimize the set of things that you really want to understand and trust. And so when it comes to TDX, right, those that are within the bounds of the TD, so that would be the TD administrator or the virtual machine guest administrator, or if you're doing a containers and deployment, it would be the owner of the container, the administrator of the container deployment system, the guest OS that you're running on, and any applications that have access to your data. With SGX, right, what we're looking to really achieve is the sort of this smallest attack surface by only including part of the application. Well, that was his initial design framework, was to keep that the amount of application that you were really having to understand to the smallest extent possible. So that's sort of like the compare and contrast in graphical terms. But what does this mean for deployment? So when we've gone and spoken to customers, right, customers tend to fall into sort of like three groups that have application security, data security, sovereignty, compliance, privacy all in mind, right? So and their concerns will range from one end of the spectrum. I want really tight security. I want the best you can provide me with. To a well, actually, what I need is more control over the data and the sovereignty, and I'm really trying to, at most, well, not at most, but trying to remove the cloud provider. I want the cloud because the cloud offers me lots and lots of benefits, but I would prefer not to have the cloud provider, in my trust boundary, have access to my data. And so figuring a way out to improve that situation. And so there's this spectrum of needs. And so we have, technology that provides across that spectrum. You get to choose, which technology you might want to choose for which situation. So that's why we, we've gone down this two technology route, because we think there are different needs, different horses for different courses, as we would say. And so what I now want to do is really talk a little bit more in detail about what the TDX architecture is and what's to come, because I think that's just as important as we move forward. So I've got a couple of foils to try and summarize the overall TDX architecture. There's a very, very good white paper, and you'll see a reference, and I'm sure links have been handed out to this already. There'll be a QR code for the website eventually, but there's an excellent white paper that we've just updated on the TDX architecture. You can find that at the site that we'll talk about towards the end. But that white paper goes into quite a lot of detail. What we'll do here is just summarize the different aspects. So at the heart and soul of TDX is this new software module, which we refer to as the TDX module. Now, the TDX module runs in a new mode of the processor, which we call SEAM, and SEAM is the secure arbitration mode. And so SEAM requires the TDX module to be loaded into it. SEAM itself provides protection to the TDX module, and only loads TDX modules that come from Intel. Now, The TDX module operates as a peer to the virtual machine monitor. Now, it's not a full virtual machine monitor. It doesn't manage resources of the platform. That is still the role and responsibility of the VMM. But the VMM gets to call upon the TDX module to build out virtual machines in scene mode. So, and those virtual machines we refer to as shorthand as a TD. So we provide two new instructions for the VMM to call into the guest software interface that, also the host software interface, I should say, that the scene module will offer out to the VMM. So typically what will happen is a guest says, I want to instantiate a TD. The VMM will allocate pages from regular memory that are to be used by that TD, and it will give those to the TDX module. And the TDX module will then assemble the TD. Now, in order to provide protection to those pages that are given to it by the VMM, we have two new hardware capabilities. The first is a set of page tables, secure page tables that are only accessible from the TDX module. And those secure page tables allow the TDX module to identify which pages in memory belong to which TDs. From that, when memory references are made, when a memory transaction goes out to the DRAM, it's going to access that DRAM through an encryption engine, and it needs to decide which key to use, and that's based off the identity that's associated within the SEPT. And the TDX module is responsible for programming the keys that are in the hardware. And then that gives us now isolation of a TD's memory space from another TD using the page tables. And then the encryption and other access controls will provide separation from the virtual machine from what we call the shared space of memory, which is the non-TD world. Okay, let's go to the next page. So let's talk a little bit more about the memory encryption and integrity protection that we placed. So the way the TDX architecture works is it uses the multi-key total memory encryption engine that we have in our platform. We introduced that with Ice Lake, our third generation Xeon. And the number of keys that you can have access to varies from platform to platform, and they increase over time. What we also do is we add into the hardware a bit that tracks ownership of in memory reference terms. This is always cache lines. You always write out to memory in 64 byte blocks, and so each cache line is tracked to know whether it's a TD, it belongs to the trust domain or not. Now, when TDX module is first booted up, the TDX module uses a special instruction to actually go and generate and insert keys into the memory controllers that sit within the platform. And then as references come in and out, they'll reference which key ID they're to use, and then that gets loaded automatically into the hardware and gets decrypted. Now, what happens if regular software tries to write is programmed to write to that direction. So there are a number of controls that we have to prevent that, so or to catch it. So in the hardware, there was this TD bit, remember? So when you use a non-TD key to write to a location, that TD bit gets cleared. Now, if you then try to consume that line from within a TD, you're expecting that bit to be set. And so if we have a mismatch, that will fire off an error condition, and the error processing within the TD module will occur. If you used the wrong key ID from a different TID, you would actually get a different site. You would get different text. Now, obviously, that would also result in a bug in the TDX module, because the TDX module is using the page tables to keep the TD separate. But there is an enhanced mode that we have in the next generation called cryptographic integrity mode, where we also store a 28-bit SHA-3 based MAC within the when the memory is written to out to DRAM. Now we can do this because we essentially consume some space from the error correction data bits that are reserved in the DRAM. Now, there is this trade-off you now have, right? You have better integrity for these different types of attacks. Also, helps in the rowhammer space. But the trade-off you get is you get less coverage from an ECC perspective. So you have to make a decision about how much ECC coverage you want versus how much security you need. So that's the only trade-off we have. There's a trade-off we have in that space at the moment. So that tells you a little bit about what the TDX architecture is supposed to be, right? We've been working hard with a number of cloud partners, and we made this announcement as we were launching our 4th generation processor. So this is codenamed Sapphire Rapids, that we're bringing TDX through these partners to availability first, and then that we would have general availability of TDX and the next generation of processors called Emerald Rapids next year. So that's what we have, and I think what I wanted to do was spend a little time talking about what's to come. So, and you will see new architecture documents have been released for some of these features, for these features that I'm about to talk about. These are all appearing. So the first one is called TD partitioning. So in sort of the base case on the left-hand side, what we refer to as TDX1, you have to enlighten the guest OS to run inside the TD, and that's work that's got to happen. But we've also looked at finding ways to wanting to run unenlightened guests, and the way that we're expecting the ecosystem to go and do this is by taking a reduced form virtual machine model or some other form of abstraction to do the enlightenment piece itself, and then allow you to put in unenlightened guests. And so this would be very, very helpful, especially in sort of the enterprise space, where you're going to rely on lots and lots of applications that are maybe running on old operating systems. So this will allow you to pick up and shift old applications that are running on old operating systems into the new world. And then we're also seeing requests to support other types of capabilities in amongst the unenlightened guest with some other sort of device driver or something along those lines that will assist the guest. And so this is what this extended and unenlightened guest use case is all about, bringing new services or existing services to that guest OS. And so we very much see, the L1 VMM is the piece that gets added by software, by the TDX infrastructure. And then the L1 VMM is itself responsible for partitioning the memory infrastructure within the TD. Now, the thing to note is that this is not a full nesting case. This is a partition. So the TD offers one guest physical address space, and the L1 VMM is responsible for partitioning that up between the one unenlightened guest that you can have and the more than one. I think there's a fixed number defined of enlightened VMs that you can also have, L2 VMs that are inside the TD also. So that's TD partitioning. I'm very excited about this capability and what it enables us to do. The second thing to touch is migration. So in the cloud, you don't know where you can run, but your workload can also be moved by the CSP from one place to another. Well, if you're encrypting memory, you can't just pick up the memory and move it, or if you're trusting the infrastructure, you want to understand and be able to move your trust domain from one hardware platform to another hardware platform in a trusted manner. Now, we did release some details of this a little while back. There's enhanced details on this process, and I think we're working to get upstreamed the capability, this capability for the next generation of processors. And what this will allow you to do is support both pre and post copy migrations. Now, as a tenant, you are going to have to consent to this, right? So it's going to be visible from the attestation whether your TD is migratable from one machine or not. And if you so choose from a security policy perspective that you don't want that, then that's a conversation you would have to have with your CSP about that workload staying still. Of course, being able to migrate a TD opens up some very, very interesting attack potentials for which we have to provide protection against. So, creating a cryptographic copy and then, replaying that type of TD. I think that we often refer to those as cloning attacks. You'd be able to use stale data, and that's another form of replay, right? And then, of course, you really want to ensure that the TCB of the platform that you attested to when you had when you created your TD is when the platform that its destination has a similar, at least the same TCB, and so the architecture allows us ways to provide attestation between the source and the destination, and the cryptography to allow a secure transfer from one environment to the next. So that's migration. So another feature that was requested is and another thing that's very, very important to our cloud customers is being able to preserve uptime, and as we do updates to the system, we're minimizing disruption to our Intel's customers, so the tenant. And so we've seen this a lot, you know, as we one of the great things about the TEEs that Intel offers is that we offer this ability to, if we find an issue, to be able to attest that that issue has been addressed. But now we need to be able to do that without, you know, causing the whole system to be rebooted. This is very, very expensive to the CSP. Cost them a lot of time, money. And so what you can see in this diagram, in the top diagram, right, is we have a TD attests, and it's the TDX module is in version 1, and to get to TDX module version 2 and to be able to attest that that has occurred, you have to go through a whole TDX restart. That means you've got to tear down the TD, tear down the TDX module, install a new TDX module, and rebuild the TD. Well, wouldn't it be nice if you could actually just say, hey, I'm just going to pause the TD for a moment. I'm going to swap out underneath you a new TDX module that you know, addresses any problems that might occur. And so that's the approach that we've taken with the TD preserving updates. We give the VMM the capability of saying, just hang on a second, tear down the TDX module, I should say. So tear down the TDX module, install the new TDX module. Now, TDs that existed before that process now get to attest to two things. They get to attest to the TCB before the module update and the TDX module after the TDX module update. And then new TDs would just attest to the current TDX module update. So that's something that's very, very important. It minimizes disruption to yourselves, and that's a key requirement that's coming from our CSPs. And then this is really future stuff. I believe Greg made a note of this in his keynote, which is in the architecture that we have today, TDX is very much bound to memory-only operations, and you have to do this double buffering. And we've seen presentations from you know, people wanting to use different hardware devices for acceleration of certain types of workload. And in order to really go and drive a better story in this space, Intel and a number of our hardware partners have been working very, very hard in the standard space to really address how we can enable trustable devices to have access to memory of a TEE. And so TDX Connect is the architecture that we're putting forward to do that. It's based on PCIe, the PCI SIG in TDISP standard that allows you to provide integrity and encryption between device and the platform, and then SPDM from the DMTF, which provides device attestation. And you combine those together, and you can allow a device, once it's trustable, inside the actual TE memory interface. More detail, you know, we've published some specifications in this space, and I think there is a new architecture spec that will be up very, very soon in this space also. So that's really exciting. Now, I did reference this earlier on. There is a website for us for you to go and check out. Hopefully, one of my colleagues that'll be listening to this can stick the URL into the text stream. There's a lot of documentation there. It has to be said. I would always recommend the white paper at the very, very beginning. That goes into a little bit more detail about the mechanics of the TDX architecture. And then there are new specifications. If you're certainly interested in some of the newer features that I've spoken about today, there'll be specifications for in the 1.5 space for partitioning and migration. There's also a section on TDX Connect. We're also providing linkage to security guidance that's already been published. So if you're interested in guest kernel hardening, there's some material there. And also, if you're a developer and you want to understand about transient side channels, there's links to TDX specific guidance advice in that space also. So there's lots and lots of information there, and I'd wholeheartedly recommend taking a look at that. And I think with that, I am done.